Hi, everyone. Welcome to Explaining Explain, a dive into PostgreSQL explain plans. Thank you for joining my talk. My name is Richard. Just a little bit about myself. I am a support engineer at Enterprise DB, which is one of the leading Postgres database companies. We provide services to many clients. I've been working there since 2015. Previously, I was working as a Perl web developer and then a DBA. And I've been using PostgreSQL since version 7.4, and now we're at 15, so it's actually been quite a lot of changes since then. Real quick about EDB, like I mentioned, we are a professional services company. We also produce a lot of products for the PostgreSQL community. We provide database system support. We provide remote DBA services for people for companies that don't have DBAs. We also provide professional services to help with things like migrations and implementing a lot of the products that we have to offer to our customers. We're also very involved in a lot of community projects that we contribute to. Namely the PostgreSQL engine, which many of you are familiar with, backup applications like Barman and PG Backrest, and also PG Admin and the pooling software, PG Bouncer, and a lot of other projects as well. So as a support engineer, one of the most common questions that I get from our customers is, why is my query slow, or why is my database slow? And there could be a lot of reasons for that, and I think the first way to deal with any kind of performance issues is check with Postgres and ask it to explain what's going on with the queries that you're running. Now, I realize that some of you guys, some people may not know how to get the queries to begin with, because a lot of times those queries are being formulated by an ORM. So what I would do first is you want to toggle one of two or both configurations parameters. The first one being log min duration statement. If you can change log min duration statement to something like 0 or something, maybe like 100 or so. This is in milliseconds. So any query that runs for more than, if you set it to 100, more than 100 milliseconds, then it'll get printed to the PostgreSQL log. And in this case, I set it to 0, then all queries will get printed to the PostgreSQL log. So you can see, what the ORM fed to the database and what queries got run. The second parameter is log statement, and this is a choose one or the other one. So it's all, mod, DDL, or none. The default is none. You can change it to DDL, so any kind of alter statement or create table, create index, those kind of statements will get logged to the PostgreSQL log as well. To use mod, that will print only the modification DML, which is insert, update, delete, truncate, things like that. When you use all statements get logged. Now you may wonder, what's the difference between log statement and log min duration statement? Log statement prints the query that gets issued before it runs. So when the ORM feeds it, and before PostgreSQL runs the query, it prints that query to the log. And if somehow that query crashes the database, at least you can go to that log and find out what ran before the database crashed. Log min duration statement, however, prints the query after the query has finished. And it includes a duration saying, it took me this long to finish this query that I'm printing now. Okay, so set one or both, but be aware that when you set it to all or 0, you could generate a lot of I/O on your disk. So you could end up with some kind of performance degradation there. So you don't want to keep it on 0 or all the time. Okay, just as important is setting the log line prefix. While I'm at it, I wanted to give a plug about this parameter because it's one of my, I think this is one of the most important parameters from a developer or a debugger standpoint. I have another talk on this, but just quickly, I would change it. The default that Postgres sets is just a timestamp. And that's just a general community philosophy. We want to keep everything minimal so that way people don't have hurdles starting it up. So setting this to timestamp followed by a process ID, followed by a line number and a transaction ID, user database, application name, and then the client IP address or host name. This will help you tremendously when it comes to debugging query issues, especially if you have many sessions or many web servers connecting to the database at one time. Okay, so please make a note of that one. And so just moving on. So once you've got the queries, how do you deal with, how do you use explain to your advantage? Okay, so we're going to go through the following points in my talk. Okay, first we're going to talk about what does explain do, and then second we're going to talk about how does explain work, and then we're going to talk about how do I interpret the explain output. Okay, and then finally I'm going to give a lot of several non-trivial real-world examples of how explain can help you in developing your applications. Okay, so just starting off, so what does explain do? So explain, it is a feature of Postgres where you just take a query and you add the word explain to the front of it. Okay, and what it'll do, it'll print out a query plan for you. And it'll show you, oh, I'm going to use this index, I'm going to use this kind of join method, and all the stuff that it does to get you that output to your application. What you can also do is you can use explain analyze with your query, and what that will tell you is what Postgres did for your query. So it might estimate, like, you know, I want to select star from this table, and I know that there's 100 rows, but and it'll print out that estimate in the explain. But then when you actually run it, it'll show you how many actual rows that it took and how long it takes to do that scan or that access. Now, what does explain not do? What doesn't explain do? First, it won't explain why a query planner made some choice. So if you had a choice between a sequential scan and an index scan, it's not always the index scan that wins. The query planner uses some statistics, which I'll get into, to make that choice, but it won't tell you why you made that why it made that choice. So it's up to you to figure that out later, and I'll kind of help you guys with that as we move on. The explain doesn't tell you about query performance being affected by another session. So if you have several sessions talking to your database, trying to access a particular table, and it suddenly gets slow, explain won't tell you that. So you have to use some extra tooling to figure that out. It won't tell you about stuff that's happening outside the database. So like, let's say you've got your OS that's running like an antivirus or something like that, and it's pegging your disk, and just getting data off your disk is really slow. It won't tell you that. Okay. And then finally, it won't tell you things that are external to the database in general, or the server itself, like things like network latency. You know, if you have your laptop here in San Diego and you're trying to run a query that's, you know, on a server in Japan or something like that, that latency won't get captured in the explained output. Okay, so basically it just tells you everything that Postgres is going to do under the hood, and any additional latency that you calculate is going to be outside of Postgres, and you'll have to do extra tooling to figure that out. Okay, so moving on, how does a query planner work? Okay, so like I mentioned earlier, Query Planner uses a cost-based approach, using some statistics and do some calculations and deciding which method to take when working on a query. So those statistics are stored in a table called PG statistic. It is a meta table. It has data that is not very human readable. It's all histogram data. If you want to try to figure out what's in there, you can use the view called PG Stats. That might be helpful, and I won't get into that. That's beyond the scope of this talk. Now, to refresh the statistics, you want to use a command called analyze. So you say analyze and then you just press enter, and you analyze the entire database. You just type analyze a table name, and you analyze the table. Now, don't get this confused with explain analyze. Explain analyze is taking the explain and then analyzing that that query to give you output. The analyze command by itself refreshes statistics in the database. Okay. All of this stuff that's cost-based is tuned by the configuration, and you will find in your PostgreSQL.conf file things that say like enable underscore something or something underscore cost. Okay. There's a lot of configurables. This is the list of all of them, and I don't think it's a bit intimidating to look at. And if you want to kind of poke around, you can read up on it in the documentation. However, for the most part, when I work with our customers, we generally deal with these two parameters: random page cost and sequential page cost. Random page cost is the estimated cost of a random fetch off of the disk. So I have an address, and I say, oh, I need to get this this item off the disk at this address. That's a random page. Okay, so it works well for SSDs, but it does not work well for spindle disk. Okay, sequential page cost is the cost of accessing a page in sequence. So when I do a sequential scan or a table scan, how much does it cost for me to get a page out of the disk? Okay, now these costs, they're kind of arbitrary. They're all relative to one another. So there's no like absolute like measurement like IOPS or disk speed or anything like that. It's just basically as a DBA, the DBA will set up a database and say, let's just consider random page cost to be cheaper than sequential page cost. Or in some cases, they might say random page cost is more expensive. So they can tune it up and down however they want. Okay. Okay, so that's config. So we're going to go and start looking at some real explain output. Okay. And what I've done is I've taken this tool called pgbench, which is a benchmarking tool that comes out of the box with Postgres. And it's just a basic, I just set up a basic test. Okay. So pgbench I is initialized, just create 4 tables, one table with 100,000 rows, another table with 1 row, and you can run some benchmarking tests on that. So, but we're not going to do that. We're just going to do some selects on that data that gets generated. Okay. So the first thing I'll do is I'm going to run explain select star from pgbench accounts, join with pgbench branches on the BID column, where AID is less than 100,000. Now, like I said, it's going to be 100,000 rows. AID less than 100,000. That means I'm going to access the entire data, entire table. And what you end up here is the output of nested loop, which is joining 2 sequential scan outputs: sequential scan on pgbench branches and sequential scan on pgbench accounts. Okay, and that's good. Okay, so we see something like cost. So you might be wondering what cost is about. So the 2 numbers of cost, the first number you see is 0, and that's the amount of cost to get to the first row that you want to return to the application. The second number, which is 4141.00, is the amount of time that the amount of cost that it takes to the entire data set back to the application. Okay. Okay. So now I want to zoom in on this particular number right here, which is 2890. How did a sequential scan on pgbench accounts cost 2890? Okay. So we're going to go to the next slide here. And keeping that in mind. So the way that we're going to calculate cost, okay, is going to be the number of blocks times the sequential page cost, which is in the config, plus the number of records times the CPU tuple cost, which is in the config, times the number of records, plus the number of records times the CPU filter cost. Okay. Now, okay, and then we'll get some statistics here. So the relation size of pgbench accounts, which I'm going to pull out of this this function, is about 13 megabytes. Okay. Now block sizes, if you don't know, the standard block size on disk is 8 kilobytes. Okay. And then so if I take the relation size divided by the block size, I'm going to get 1648 blocks. Okay, so that's what I can plug into that first set of parentheses. The second set of parentheses is number of records. So I know there's 100,000 records, and then I multiply that by the CPU tuple cost. And then the third set of parentheses is the number of records times the CPU filter cost, which is the cost. CPU tuple cost is the amount of cost we have decided that it takes for the CPU to process one row. And then CPU filter cost is the amount of cost that it takes for the CPU to decide whether I should filter this row out or not. Okay, and you add that all together, you're going to get 2890, just like you saw in the explain output. Okay, so hopefully that makes sense. So as you can see, it's all cost-based, all statistics. You tune CPU tuple cost up and down. You tune sequential page cost up and down. You're going to affect the costs that are estimated by the query planner. Okay, so that was all just estimations. Okay, now when I do explain analyze, not only do I get the cost, the exact same cost that I got earlier in the other screen, I get this other set of parentheses, which is actual time, actual rows, and actual number of loops run. So what this means is basically when I ran this query, this is what I encountered. I encountered one row in pgbench branches. I encountered 999,999 rows in pgbench accounts, and then I joined them with a nested loop, and it took me 61 milliseconds to do that. Okay? So to a developer or a DBA that's trying to solve a performance issue, this actual time or actual number of rows is the most interesting thing for us to look at. Okay, and these times are all done in milliseconds. So it took 0.026 milliseconds to do a sequential scan on pgbench branches and so on. And notice that we did a nested loop. Okay, now I'm going to come back to this in a bit, but nested loop is one of the join methods to take the two tables and join them together. Okay, now I talk about explain, I talk about explain analyze. There's actually a lot more that Postgres offers. And another one that you might be interested in is with buffers. So if I tack on the word buffers to the explain call, I'm not only going to get the estimates, the actual stuff, but I'm also going to get these things called buffers, shared hit, shared read. The buffers is basically the cache, okay? And when I say I had, when I run this query and I hit 2 buffers, then I hit two 8 kilobyte blocks in cache, and I read 1638 off of the disk. So as you can see in this call, I actually made a big read off of the disk, which might have been slower. So that means if I ran this query again, instead of 61 milliseconds, I might actually get something a little bit faster, depending on how much memory I have. Okay, and you add them up together. So shared hit on pgbench branches and pgbench accounts, 1 and 2 equals 3. So the nested loop, you're going to hit 3 buffers. Okay. Okay, I'm going to move on. So the building blocks of these explain plans. Okay, scans and joins. So if you look at the pgbench accounts table, is 100,000 rows, and all the BIDs are 1. Okay, so let's say I actually updated it so that the BID matches the AID. So then they're all unique. Okay, and when I do explain analyze here, and I want just BID equals 1, I'm supposed to only find 1 row. Now the reason why in this output you see is a sequential scan is because it doesn't know what is stored in the table. Okay, and that's why we need to have indexes. Okay, so when we have indexes, we actually create a summary of the table based on a particular column. So here I say create index on pgbench accounts branches BID. So in this index, I'm going to have a bunch of addresses of all the rows in the table, followed by all the different BIDs, and then when I run this query again, I'm going to actually get an index scan. And the reason for that is because all I need to do is go to find the one page one spot on the index, find out the address, and then go get the random, do a random fetch off a disk to get that one row. Okay, that's so much faster than scanning the entire table. As you can see, the execution times dropped from 45 milliseconds to less than 0.2 milliseconds. Okay. Oh yeah. Okay. I'm sorry? I didn't. Mm-hmm. Oh, the planning time went up. Yeah, you're right. I don't have an explanation for that just yet. I think it might have something to do with. Well, I actually, I'll explain it to you later after the talk. Okay, but yeah, the planning time does go up in certain cases. Okay. It could have been just my laptop running some cycles on Chrome or something like that. But okay. So we talked about sequential scans, we talked about index scans, and then we also have this thing called index-only scans. Okay, if you notice here, when I do a select, the same parameters, AID is less than 1,000. The index scan call was 0.8 milliseconds, but then the index-only scan was 0.237 milliseconds. Why is it different? It's the same filtering, right? AID less than 1,000. The reason for it is because of what columns I selected. Okay. Now, when I do select star, I want all the columns in the table, and I'm going to get all that data back to my application. When I do a select AID from a table, all I want is just that one column, which also happens to be the column that I indexed on. Okay. So when I say I want all the AIDs less than 1,000, it just scans the index, and it finds all of them, and then returns all those AIDs to you. Whereas for the select star, it finds all the AIDs less than 1,000, and then it gets all the addresses, and then it goes back to the disk to get the rest of the columns for you. Okay, so that extra fetch from the disk is very expensive. So the reason why I wanted to point that out to you as developers is that we really need to be very careful about what columns we're going to pull. Okay, and sometimes the ORM might pull more than you want. And if you can somehow force the ORM or trick the ORM to getting just the columns that you need, you could end up with a faster query. Okay. So I talked about several of the scan types: sequential scan, index-only scan. There's also the bitmap heap scan, which I didn't talk about, which is basically somewhat of an index scan, but not quite. What it does is it basically scans the index and it builds a map of all the pages that you need to fetch from disk. So basically, if you have a bunch of rows that share a page, instead of going through each row and pulling it off of the disk and doing fetching that same page many times, you look at the mapping that was created and you say, oh, I'm going to do this, fetch this page off of disk, and I'm going to happen to pull 4 or 5 rows at a time instead of 1 at a time. Okay, and that actually speeds it up too. Okay, so that's the scan types. Now, we're going to do a little bit more with this pgbench database. So I'm going to insert into pgbench branches. Okay, so now there was only 1 row in pgbench branches. Now there are going to be 100,000. Okay, and then I'm going to do the same query that I've been running before. I'm going to join accounts and branches, and then I'm going to filter on AID less than 100,000. So what do we get here? What we get here is a hash join. Okay, it wasn't the nested loop like before. And the reason for that is because we've actually created more data, and the query planner has decided a hash join might be more performant than doing a nested loop. And I'll get into that a little bit more in a moment. But I can actually I can force the query planner to choose the nested loop. Okay, the way to do that is before you call the query, you call set and then enable hash join to off. So you tell the query planner, don't do hash join. You can do anything else you want, but just don't do a hash join. And notice how I'm doing this within the same session. So I'm not making a global change in the config. I'm not affecting other users. I'm just affecting my own session. Okay? Oh, okay. So when you do that, you run the explain analyze, and you get, this time, a nested loop. And the reason why it chose the nested loop, it didn't choose nested loop because it's expensive, right? So if you look here, it says 41,000 costs versus what we had earlier, which was a 4,000. So it's a 10x improvement by doing the hash join. Okay. Now you may wonder, why am I using a sequential scan? I have an index on this table, so why am I using a sequential scan? The reason for that is because I'm choosing AIDs less than 100,000. I'm going to read the entire table anyways, so why bother doing the extra work of looking at an index and then pulling off the disk after looking at the index? Why not just get everything off the table anyways? Okay. All right. So I'm going to move on. Okay. So, okay. Sorry, I'm running a little short on time. So, this time, if I reduce the search from 100,000 to just 100, I'm going to run into a different query plan, which is using a merge join instead, and that is definitely going to be a lot less costly because I'm only looking for 100 rows or 100 values, and index scan makes a lot more sense. Okay. Now, the index is already pre-sorted, so then I can do a merge a lot easier. So just quickly on the joins, nested loop, like you saw earlier, it works well if you take a table and then you join another table. For every row in this left table, you're going to scan through the right table and then move on. So that's how the nested loop works. Now, it's fast to start, right? You don't have to set up anything. You just immediately start scanning on the disk and looping through the values. It works best for small left side tables. Okay, if you have a large, a table on the left with lots of rows, and it's going to be very expensive. Okay, the merge join, which you just saw, it basically takes a zipper operation on two sorted sets. So if you have an index on both tables, on the related columns on both tables, it's already sorted. So you just zip them up together, match them all, and find the ones that you want, and then return the data. So that's good for large tables, especially if it's already sorted for you. Okay, and then finally the hash join, which I briefly mentioned. You basically take the right side values and you build a hash of all the values in that in those values that you're filtering on, and then you scan the left table to find the matches. So this only works for equality. It doesn't work for like greater than, less than. It doesn't work. I don't think it works for like similarity on words and stuff like that. Okay, high startup cost but fast execution. Okay, so. This is the final part of the talk, which is I wanted to share some real world examples of where explain can help you. Okay, so let's say I create this index and then I run this query, select star from PGBench history where AID is less than 100. Now we see that there's a big misestimation. Okay. And you're doing a sequential scan, and the second one I use index scan. And why? It's because the estimates were off. Remember how those values in PG statistics are the values that the query planner uses, and you use analyze to refresh those statistics. When you create an index, the index is created, but the statistics might still be off, so that the query planner might think, oh, I don't want to use the index because it's too costly to do so. Okay, so whenever you want to do, and after the analyze, you see that the rows were same order of magnitude, so it's more correct. And now it uses an index. So the tip here is you want to make sure that your database is vacuumed and analyzed often. Okay, so you want to make sure you tune out of vacuum. Have your DBA do that if that's not your responsibility. Okay. There are some situations like these where the statistics are off, but not because it was a bad estimation, but it was because there are correlated tables that the database does not know about. Now, we as human beings know that cities belong to states, right? And we know that children are not as tall as adults, okay? So when you have things like city and state columns, the database doesn't know that it's related. When you have a height and weight and age column, you don't know, the database doesn't know that they're related, okay? Now, you can tell Postgres and kind of teach it and say, hey, these two columns are related. And based on those relationships, it might be able to make a better query plan for you. So I won't go into the details on this, but using the create statistics to create extended statistics on your tables might actually help you with your query plans. Okay. Another example of where explain was helpful. Now, this query takes a long time, and we don't know why. And when we run it on explain, analyze, we see that, hey, there is an external merge to disk, and we're using 2 megabytes of disk. Now, that doesn't seem like a lot, but when you do it, at scale, and you're doing, hundreds and thousands of these external merge to disk 2 megabytes at a time, it could slow down your application. Okay. Now, the reason why is because there's not enough memory available to do that last sort at the very top. Okay. And if we look at the work mem value, it's actually just 4 megabytes, and that just happened to not be enough, right? So we increased that to roughly like, I basically in this example, I just quadrupled it just for good measure. Once I increased it to 16 megabytes, ran the query, all the sorting was done in memory, and it was a lot faster. Okay, so use the explain output to help you figure out if you're doing a lot of I/O on disk because of sorting or temporary files. Workmem, I'm not going to get into the tuning too much, but it can be done on a per session basis as well, just like those enable, disable calls I had earlier. Okay. Another example of where Postgres explain plans help. Okay, so I have this index, and I created it on substring on the filler column, and I just want the first value. Now, when I run the select on this table on pgbench history, where this query, and it's slow, right? And we don't know why, right? We run explain on it, and we see that hey, it's actually not doing the index scan that I want. It's actually doing a bitmap index scan. And then I changed my query, and I use substring lower on filler, and it's still not doing it, and it's still not performing very well. Now, the reason why is because when you want the query planner to use an index, it needs to be called in the same way in which it was created. Okay, so those other examples that I had, it was not substring on filler, it was left on filler, or substring on lower of filler. And by doing that, the query planner doesn't know I should use that index. Okay. And once you call it the right way, you actually start using the index scan like you're supposed to. Okay, another example with JSON. Okay, some other situations, which I'll go through pretty quickly. Prepared statements. If you are using prepared statements, I know, I forget if Django uses prepared statements, but I know in Java and Perl, there's this idea of using prepared statements, and whenever you call execute on a prepared statement, you actually are using a custom query. The query planner creates a query plan for that execute call. Okay. Now, after you call execute 4 or 5 times, it starts using a generic plan because it doesn't want to spend the time to create a new plan for you because that's just extra processing. Okay. Sometimes that works well, especially if you're doing like a bulk load or a bulk update, but sometimes that doesn't work very well. And what you want to do is, when you look at the explain output, you'll see that, hey, we're using a generic plan instead of a custom plan. Okay. and you can adjust that with the plan cache mode parameter. Okay. Other situations where you might have a poor performance is when you get the join order wrong. Okay. So in this example on the left, if I call select star from A, comma B, comma C, where, and then all my where clause, the database, the query planner can reorganize the order of those tables based on how it sees fit. If you know that, for this thing I want a nested loop, and I know that this table is a lot smaller than this other table, you can tell us explicitly left join B, A join B, so that A is always on the left side. Okay. Now, the caveat to that is if you have too many tables that you're joining together, you might run into the problem where the join collapse limit or the from collapse limit is reached. Now, these two limits that are in the config, they basically are a threshold. If you have more than this many tables, like let's say 8, if you have more than 8 tables, then it'll preserve the joins, and then sorry, I got that mixed up. It will reorganize based on what it knows to see if it could help you find a better performing query plan. And after the 8th table, it's just going to tack them all on. Okay, and then what you might end up with is some really poor performing queries. If you increase the from collapse limit or join collapse limit, it'll spend more time looking for the best permutation for you at the expense of additional processing time. So you may or may not want to adjust these limits accordingly. In version 10 and above, there's this idea of just-in-time compilation, where under the hood, Postgres does a little bit of pre-compiling to help improve some queries, and it only seems to work well in data warehousing queries. So if you have like a web app or something like that, you may want to just turn off this just-in-time compilation. Okay. My final example is ORMs. So as we all know, Django uses ORMs. Now this particular example is not from Django, but we did have a situation where the customer complained to us saying, hey, this query took too long. And 40 milliseconds is okay when you're doing development, but in the production environment it was not. But then when we ran it, we only saw it run in 0.25 milliseconds, and we were wondering why. And the reason for that was because the ORM was casting a data type. Okay, it was supposed to be a numeric type, but the ORM was casting a type to double precision, and there's no way for that for Postgres to do that index scan and comparison. Now, how do we know this? Right, because all the examples that I've shown you so far are using a console. Like if you're using pgadmin or PSQL, you type in the query and you tack on explain, and then it spits out this output for you. Now, if you are in this situation where you're trying to run an app and the ORM's generating all the queries for you, and you don't know what's going on, there's this extension called auto-explain. Now, this is a very, very useful extension, and I encourage you guys, I encourage all of you to use this. It basically prints explain plans to your log, and you can tune it to add analyze at a certain threshold. If this queries take more than 1 second, print out the explain analyze output. You can tack on the buffers and stuff like that as well. You can actually do it on a per session basis with load auto explain. So you just at the beginning of your connection, you can load up auto explain and have it print everything to the log. It creates an additional I/O to disk, so you don't want to use this in a production environment for very long. Okay, so that's it in terms of all of my examples for you guys, for everybody. If you still need help with your queries, you can look on Slack. There is a community Postgres Slack. There is also IRC if you are familiar with IRC. And then you can also send questions to the PostgreSQL general mailing list. And There's also a PostgreSQL table outside, so I encourage you guys, I encourage all of you to drop by, ask your questions if you want. There's actually a book that we're giving away. It's called the PostgreSQL Administration Cookbook by one of our coworkers at EDB. It pretty much gives you a bunch of steps on how to diagnose different situations when you use the database. Okay. Thank you very much.
Thank you, Richard. We have a few minutes left for questions.
Thank you. Great talk. I'm curious, you mentioned vacuum very briefly. Could you talk a little bit about what that does as opposed to analyze, and do you need both, or does one kind of cover is there overlap there? What's the use case for each of those?
Sorry, I'm actually hard of hearing, so I might.
Oh, sorry.
Yeah.
So I'll try and talk more into the mic. Could you talk a little bit about the difference between analyze and vacuum, and when you might use each?
Okay. So vacuum, what that does is it cleans up your tables. Whenever you delete a row or update a row, it isn't actually overwritten. It's actually just flagged as invisible. So that way, multiple sessions, they don't all see the same data. They only see the data that they affected. Okay. So when you flag those things as hidden, you end up bloating the database. And when you do that, future scans or future selects, they can get really slow because you're going to try to scan more than you really need to. Okay. So vacuum, what that does is it flags it for reuse. So future updates and future inserts can reuse the stuff that's hidden and that nobody needs to access anymore. You may want to use vacuum full if it's severely bloated, but we generally don't have a situation where we have to do that. Especially if you've tuned out a vacuum in a way that it does it correctly. Analyze will scan the table and update the statistics. When you do updates, I think if you do a lot of many sessions and they try to update the table, sometimes the statistics collector can't keep up with it. So then the actual statistics stored on the table gets a bit inaccurate. So doing analyze will keep that up to date and fresh. Okay.
Any more questions? I think there are no more questions. Please give another round of applause to the speaker.